A very good morning, one and all. I am Dr. R. Purushothaman, Assistant Professor, Department of ECE, JJ College of Engineering and Technology. In this slide, we are going to discuss about the concepts of linear integrated circuits, some comprehensive overview of linear integrated circuits. Of course, the linear integrated circuits is an electronic circuits built on a single semiconductor chip that processes continuous time, that is analog signals. They are characterized by a linear relationship between input and output signals, meaning that the output is a scaled or modified version of the input. There are some key characteristics in linear integrated circuits that is said to be linear relationships. We have then analog signals, versatility. These are all some key characteristics of linear integrated circuits. Now we are going to discuss some characteristics of linear integrated circuits one by one. First of all, introduction to operational amplifiers. The introduction to operational amplifiers, the operational amplifiers plays a very important role in linear integrated circuits. The operational amplifiers are a fundamental building blocks in analog circuit design. They are high gain electronics voltage amplifiers with differential inputs and single-ended outputs. This is the schematic representation of the operational amplifier. In operational amplifier, we have non-inverting input and inverting input. Then this is the output. Again, I am repeating: inverting input, non-inverting input, and this is the output. This is positive supply. This is negative supply. These are all the this is the schematic representation of operational amplifier. The operational amplifiers are versatile, and it is used in a wide array of applications including signal conditioning, filtering, and instrumentation. This is the general operational amplifier stages. For understanding the internal structure of operational amplifier, there are mainly we have three stages. The first one is input stage, second output stage, and gain stage. Again, I'm repeating, this is the process, this is the flow you have to follow, my dear students. Input stage, output stage, and gain stage. The gain stage is nothing but the intermediate stage of operational amplifier stages. The input stage, in the input stage, the differential amplifier that provides high input impedance and common mode rejection. The output stage is totally different, totally the vice versa concept of input state, that is low impedance state that drives the load and ensures the amplified signal that can be delivered without the significant loss. The gain stage here amplifies the differential signal to higher voltage level, provides the bulk of operational amplifiers voltage gain. Then operational amplifier configurations, open loop and closed loop configurations are there in the operational amplifier configuration. This is open loop configuration and this is closed loop configuration. In open loop configuration, there won't be any feedback. That is, in an operational amplifier configuration, the op amp operates without any feedback. See, from this schematic representation, we may identify that there is no feedback here in open loop configuration. So it provides the maximum possible gain but is highly susceptible to noise and variations. Some key features are extremely high gain. It is very sensitive to input changes and not stable, that is prone to oscillations. This is the diagrammatic representation of open loop configuration of operational amplifier. The AOL is nothing but open loop gain. A is nothing but gain, and OL represents open loop. This is inverting terminal, this is non-inverting terminal. So if you are giving input to the inverting terminal, means inverting input, inverting amplifier, and if you give the input to the non-inverting terminal, means that is said to be non-inverting amplifier. Then VD is nothing but difference in voltage, then V naught here is nothing but output voltage. The difference voltage can be calculated by the difference between the input voltage and the output voltage. The input is the difference of two voltages, that is V1 minus V2. The V saturation is this is positive saturation and this is negative saturation. An operational amplifier configuration, that is second configuration, closed loop configuration. The closed loop, for it is meant for stability and precision. In closed loop we have feedback. From the diagram itself we can understand that in the closed loop we have feedback resistor. Here negative feedback reduces but improves the stability, linearity and bandwidth. This precisely controls the output. So we have two categories in both closed loop and open loop configuration, that is inverting amplifier and non-inverting amplifier. The inverting amplifier, here the output is amplified an inverted version of your input. Suppose if it is minus mean, then the output you will be getting positive. If the input is positive, the output you will be getting the minus. Then non-inverting amplifier, here is output is an amplified version, only that is only the amplified version of your input and not the inverted version. Next we are going to discuss about the instrumentation amplifier and the design applications for sensing. The instrumentation amplifier is meant for design applications and for sensing. This is nothing but the amplifier is a type of differential amplifier with input buffering, which increases the input impedance and minimizes the load effects. This is the schematic diagram of input instrumentation amplifier. The instrumentation amplifier comprises of three operational amplifier. See the diagram, A1, A2 and A3, and the input and this is invert, and this is the input given in the operational amplifier A1, and this is one more inverting input given in the operational amplifier A2, which is coupled in this one, and this one is coupled here by using the resistor, and the output here is again coupled to the input part of A3, that is one more amplifier. This is the output part V0. Here the main features of instrumentation amplifier is high common mode rejection ratio, that is CMRR, then high input impedance, then adjustable gain. The concepts of CMRR, high input impedance and all, already we have discussed in the electronic circuits and design subject, and the application includes the precision measurement in industrial and medical settings. Then one more comprehensive overview of LIC is that phase lock loops. The PLL is a core principle and operation of PLL. Here we have three components: VCO, that is voltage control oscillator, loop filter and phase detector. Again I am repeating: voltage control oscillator, loop filter and phase detector. The voltage control oscillator generates a signal whose frequency is controlled by input voltage. Then the loop filter removes high frequency components and stabilizes the loop. Then the phase detector compares the phase of the input and VCO signals. This is used in frequency synthesizers and frequency modulation and demodulation and clock recovery. Next we have digital to analog converter. This is a one of the type in digital to analog converters. The DAC is nothing but digital to analog converters. R2R ladder type and switching mechanism. This is R2R type, and this is the schematic diagram of R2R type. The block consists of R resistor and 2R. The representation looks like a ladder. That is why it is called as R2R ladder type. This type of DAC, I mean digital to analog converter, that uses a repeating pattern of resistor values, that is R and 2R. This is the output, and RF here is nothing but feedback resistor. MSB is most significant bit in the input value, and LSB is least significant bit in the input values. I would like to remind one thing: the input here is digital, the output here is analog. This is a simple design and high precision and easy to manufacture. Then we are going to discuss about the video amplifiers. This amplifier is meant for high bandwidth design and considerations. The video amplifiers are designed to amplify the video signals while maintaining signal integrity and bandwidth. This is the commercial name for video amplifiers, LM359. Here we are having the pin numbers 1 and 8 is shorted by the resistor, and the input part is given to the pin number 6. Then one more input is given to the pin number 7 with 12 volt input, and the pin number 6, again the pin number 2 is given as feedback to the pin number 6, and pin number 4 and 11 are shorted and it is grounded, and this the output you are getting in pin number 2. This is the schematic as well as diagrammatic representation of video amplifier. Again, the video amplifiers are designed to amplify, to boost up the signals, to amplify the video signals while maintaining signal integrity and the bandwidth. The key characteristics here are high bandwidth, which is able to amplify signals across a broad frequency range, and low distortion, which minimizes the alteration of the signal, and impedance matching, which ensures the efficient signal transfer. And summary of the key concepts and future trends in LICs. The future trends in LICs includes, linear integrated circuit includes miniaturization and integration, that is continued reduction in size and increased integration of the components. The next key component is low power design. The power consumption should be low, that is growing demand for energy efficient LICs for portable devices, and advanced materials, that is use of new materials like graphene and carbon nanotubes for improved performance of linear integrated circuits and its applications. So thank you, my dear students. If you have any feedback, you please mail to Purushothaman or at jjcet.ac.in. Thank you once again, and thank you one and all.